We are going to talk some more about functions, limits of functions, and sequences, how it's related to sequences, and then we're going to go on to something else. I just had one more example to do about functions and sequences. So the benefit to the sequence approach really is that it makes it easy to show when a limit does not exist or when a limit does not equal something or other. So remember, limit x goes to c f of x equal L. Last time we talked about this is true if and only if for all sequences xn approaching c, we have f of xn approaches L, right? This by itself is not terribly interesting, this theorem, but it is interesting to or it is useful to show that something does not converge, because when we negate these two sides, lim x goes to c f of x does not equal L means, well, there's actually a lot of ways to say what we said over here, and I'm actually going to say this in a new way. So this is one thing that I didn't say exactly last time, but it's equivalent to some stuff I said. Welcome back. You look warm. Not warm enough. Okay, there are many ways that the limit could fail to exist. What we said last time was the limit does not equal L. It means there's some sequence xn which approaches c, such that f of xn does not approach L. Now, there are many ways that it could fail to approach L. It might diverge entirely, or it might converge to something else. It might be unbounded. It might oscillate or something like that. Here's one way that you can write this, which is a little bit different. I'm going to say if and only if there exist two sequences. Remember, another way that a sequence can fail to converge is if it has two subsequences which converge to different values. Then the whole sequence must diverge. So that's another way in which this can happen. If and only if there exist two sequences, I'm going to say xn, which approaches c, and yn, which also approaches c, with limit of f of xn different from limit of f of yn. So this means that we have two different sequences, but when you plug them into the function, they have two different limits. That means the limit of the function cannot exist because of this business about if a sequence has two subsequences which go to a different limit, then the whole sequence diverges. All right? So this is yet another one of these. This looks very similar to some stuff that we said last time, although it's not exactly the same, because I have two different sequences here. There are some examples where it is most convenient to be able to use two different sequences. And we're just going to do one example of that form before we go on to the next section. All right, let's see if we can do this one example. This uses a certain weird function that the book likes to use. They write it this way. This sort of x inside double brackets. This is called the greatest integer function. Greatest integer function. And it means just you take, like, that is a function of x. And what it means is you take the greatest integer less than or equal to x. So the definition is this is the greatest integer, that is a whole number, positive or negative, n with n less than or equal to x. So, for example, what is the greatest integer of 1.7? It is, what do you say? This is not a trick question. The greatest integer less than 1.7. It is 1. Yeah, you just take that number and you round it down to the nearest whole number is basically what this means. Or if I had the greatest integer of, 2, this is 2. For negative numbers, it's maybe a little weird. Greatest integer of, I meant to write negative 1.5 is, what do you say? -2, yeah. You round it down to the nearest integer, all right? Okay, if you were to look at the graph of this, it looks like it's a function sort of with steps like this. A step function, they call it, all right? It goes down that way too. This is the greatest integer function, y equals greatest integer of x, all right? Anyway, I'm going to do an example concerning limits of this function. Let's talk about limit as x goes to 1 of the greatest integer x. 1 is here, of course. Just by your calculus knowledge, what would you say the limit as x approaches 1 of that function is? Or would you say it does not exist? Say it's, I suppose, you should be looking right here. The limit as x approaches 1. I suppose your choices are 0 or 1, or perhaps does not exist. What do you say? I would say does not exist, because in this case it matters sort of which direction you approach from, right? If you approach from the left, you get 0. If you approach from the right, it will be up here, you get 1. The fact that this empty circle, filled in circle, means that the true value, f of 1 equals 1. That's true. But that's unrelated to what the limit is. The limit does not exist. So this, I want to see if we can demonstrate this. This does not exist. All right? Now it occurs to me, sorry, I shouldn't have written, when I wrote this up here, I didn't mean to say not equal L. Can you scribble this with me? I meant does not exist here. I mean, certainly it does mean that it can't equal any particular value, but this is what I meant to say. Sorry about that. That limit does not exist. This used to say does not equal L. I meant to say the limit does not exist at all. Certainly, if it doesn't exist at all, it can't equal a specific value L. But the point is, one way to show that the limit does not exist is to demonstrate two sequences which approach the point that you're talking about with the property that those two sequences have two different limits. And you can see in this example that we're talking about, actually exactly the way that I was trying to think about this. When I come from one side, I get a different value than when I come from the other side. That should give you some idea about how to choose your two sequences. So in order to show that this does not exist, still doing all right? We'll find two sequences. One, I'll call, xn, approaching 1. They both have to approach 1, right? But I want to choose them in such a way that lim of f of xn is not equal to lim of f of yn. So you should think about, like on this picture, you want sequences which approach this value 1, but choose two different ones so that when you plug them into the function, you get different values from each of the two sequences. Anyone think you see how to do that? This, you have to just make this up on your own. What do you think? I need two sequences which approach 1 that are going to give me different values when you plug them into the function. Any ideas? Can anyone give me one sequence which approaches 1? If you recall from last time, my favorite sequences usually involve like 1 over n, and then you kind of move it around a little. So what do you think? 1 plus 1 over n, that's a good idea. I'll make that x, n. 1 plus 1 over n. So as a sequence, of course, this would be, I suppose, starts with 2, and then 2 plus a half, and then 1 plus a half, right? 1 plus a half, 1 plus a third, 1 plus a fourth, etc. Okay? So on the picture here, those points would be like here, right? And their values of the function would be up here when you plug those values into the function. okay? Someone give me another one so that when I plug it into the function, I get different values. What do you think? Another sequence that approaches 1, only when I plug it into the function, I get different y values. Here, the y values of those blue points are all up there, right? They're all equal to 1. Can you give me a sequence so that the y values are not all 1 like that? Yeah. N plus 1 over n? I don't think that will do what you want. N plus 1 over n would give me like 1 plus 1.
No, I mean like n plus 1 over n.
Oh, n plus 1 over n. Isn't that the same as 1 plus 1 over n? It sounds like a good idea to me, but I think that...
Yeah.
N over n plus 1.
Maybe you meant n over n plus 1? That would be...
I think that's what I meant.
Yeah, n over n plus 1 I like. Actually, I was going to say 1 minus 1 over n. That to me seems a little easier to imagine. It's going to end up being 1, but it's sort of from the negative side. Or if you prefer, you could use n over n plus 1, right? These are not the same, but they would both give you what you want in terms of appropriate behavior of the sequences. Anyway, what that looks like, the first term would be 0, and then I'd have 1/2, and then I'd have 2/3, and then I'd have 3/4. Maybe that is the same as n over n plus 1. It's close. You won't get 0 the first time, but it's off by 1. Whatever. All right, excellent. Now, just to finish off the little demonstration here, we have to demonstrate actually that these two limits are different, right? Limit of f of xn. So first I will say, what is f of xn? Well, you're going to look at these values here and just take the greatest integer of these values every time. The first one is 2, isn't it? The next one, and I think all the other ones will be 1, right? And does this have a limit? Lim of f of xn, this sequence. What's the limit of that sequence? 2, 1, 1, 1 is 1. Yeah, it just does 1 forever, apart from a 2 at the beginning. By the way, this would have been the answer to one of the questions on our test. I don't know if you remember this. There was a question about if you have a sequence which only has 2 values, does it have to, does it automatically diverge, or does it possibly converge? I think almost everybody on the test, the first time around at least, said that if it has 2 values, it has to diverge because it goes back and forth between 2 numbers. Actually, it doesn't have to go back and forth, though. Here's an example where it has 2 values, 2 and 1, only does converge because it doesn't go back and forth. Yeah, that's anyway, what about the other one? F of yn. This one will be 0. Aren't they all zeros? I think they're all zeros, right? Take the greatest integer of those fractions up there and you get 0 every time. So lim f of yn is 0, so they're different. Lim f of xn is not equal to lim f of yn, and that means that the limit does not exist. The limit of the function. Lim x goes to 1 of greatest integer of x does not exist. Excellent. All right. By the way, about the test, I'm sorry I haven't graded the your test rematches yet, or a homework assignment. I had an extremely busy weekend. Actually, I still have some big stuff going on this weekend, so but I'm going to get to that very soon. All right. Any thoughts about that example? So in a particular example like this, you want to try to somehow look at the graph or imagine what the function does and choose 2 separate sequences which do different things. In this example, you basically need one sequence which approaches from the right and another which approaches from the left. All right. Excellent. Let's move it on then. So that's all I want to say from section 4 point something. I think that was 4.2. The next section is about Continuity. A big deal from calculus, as I'm sure you remember. We want to talk about what does it mean that a function is continuous at some point. So let me just say the definition that you are likely to have learned in calculus. I don't know about you, but when I learned calculus, I learned a series of bogus definitions. Like one thing they told me, continuous means you can draw the graph without lifting your pencil off the paper, which is kind of like, okay, I know what you mean, but that's not a real mathematical definition if you're talking about me and my pencil. But the more technical, although still not entirely formal definition from calculus is f is continuous at some particular point c when lim x goes to c, f of x equals f of c, right? This means that as you approach the x value, x equals c, the y value also approaches the same value. And that means that if you imagine yourself sort of walking along the graph of this function, every time you approach a particular point, the y value is actually at that point that you're approaching. It's not like somewhere else, which would be a discontinuity is when that limit does not equal f of c. All right, so this is the sort of intuitive, the definition at an intuitive level. Our real definition is going to be just this, only I'm going to write out what the limit means in terms of the epsilons and the deltas. So here's the definition of continuous at a particular point. So f is continuous at x equals c when, for all epsilon, come on, sorry about that. I'm just going to write the definition of that limit, which you can still see at the top there. For all epsilon greater than 0, there exists delta greater than 0, such that x minus c less than delta implies absolute value f of x minus f of c less than epsilon. All right? I'm just writing the definition of a limit again. The only difference is, like, we would typically write L here to mean that the limit of as x goes to c of f of x equals some number L. But specifically when I'm talking about continuous, the limit has to equal this specific number f of c. So it's the same thing, only instead of L, I'm using f of c. This is the definition of continuous at a particular point, x equals c. All right? One thing you'll notice, this is a technicality, but I might as well mention it. Right here, usually we say less than 0 right there. That's because, I mentioned this before, this really doesn't typically come up when you're doing examples, but technically when you're talking about limits, you don't actually care about what happens exactly at the point, you only care about what happens nearby as you approach the point. In this case, it doesn't matter because if the thing is going to be continuous anyway, that means that there can't be like a jump in the function, and so the value at the same point needs to be the same as the values nearby the point anyway. So in the definition of continuity, I'll just say we don't need this part. If you put it in there, it's not wrong. It's just it is automatically satisfied when you're talking about continuity of functions. So we leave it out because it doesn't matter. All right. Let me just write equivalently. You could write this in terms of neighborhoods, or you could write it in terms of sequences like we did last time. So I'm just going to write two different equivalent versions. One is for all epsilon greater than 0, there exists delta greater than 0 such that, and I'm going to write the same thing but in terms of neighborhoods. This would mean x is in the neighborhood of c implies f of x is in the neighborhood, the epsilon neighborhood of f of c, right? So this is writing the same thing, but in terms of neighborhoods, rather than using the absolute values and whatever. We're usually not going to use the neighborhood approach, but it's nice to indicate every so often. And this one is useful. In terms of sequences, we can say, again, limits of a function can be expressed in terms of sequences, and the way that looks would be for all sequences, xn approaching c, we have lim of f of xn is f of c. All right, so if you have a sequence of points approaching the c, then when you plug those points into the function, you get f of c in the limit. All right, so this is continuous at a point. And to show that something is not continuous at a point, the easiest way to do that is, again, using sequences. So let me just say that. I'm sort of getting all this out, and then we're going to do some examples. So to show that f is not continuous at some point, you use another sort of equivalent way of saying all of this. F of x is not continuous at c if and only if. And there are a few different ways you can write this in terms of the sequences, but the simplest one would be there exists a sequence xn which approaches c, where f of xn as a sequence does not approach f of c. So that means maybe it approaches something other than f of c, or maybe it doesn't converge at all, maybe because it has two subsequences which go to different limits or something like that. There are a lot of ways that it could fail to converge to f of c. All right. Okay, great. I want to do one example of just showing that a function is continuous at a particular point. I think you'll see it's actually not much harder than any of the other, like the examples of limits that we've been doing the past few times. How about f of x equals square root of x is continuous at, let's do x equal 4. It really is continuous at x equal 4. Can we demonstrate that? Well, we need to do the whole epsilon thing. So what I'm going to say, I'll write this as a little proof here. Let epsilon greater than 0 be given. And then we'll find delta greater than 0 such that. And what I put here is x minus 4, because 4 is the value, like playing the role of c in this case. That's what the point that I'm talking about, less than delta, implies. And then over here, I need to put f of x minus f of c. So we can sort of simplify. What is f of x minus f of c in this case? Would be root x minus root of 4, right? Because the f is the square root, the c is 4. So in this case, it's root x minus 2, less than epsilon. Right. Once you get it started, though, it's really just the same as all these other proofs of limits of functions that we've been doing all week, right? So let's see. Actually, this one requires a special trick that we haven't used before. I'm going to do it in blue like I always do. Root x minus 2, you got to somehow simplify that and extract from it x minus 4. Any ideas about that one? Anybody like square root tricks? You square it? I'm not sure you can just square it like just because you want to. You have to rewrite it somehow in a way that's still equal to what you started with, right? You know, a typical one that we've done before would be if it was something like, you know, we did something like 1 over x minus 3, and we simplified that by making a common denominator and subtracting the fractions. 1 over x minus 3x. What? 1 over x, I said. Minus 3x over x, and then you combine them. This kind of thing, right? You're not allowed to just do whatever you want in each step. You have to do something which is actually equal to what you started with. Unfortunately, there's not a lot to work with here. You just have the square root of x minus 2. Anybody got any bright ideas? There's an old trick. I remember I learned this trick when I was a kid. It was a trick related to the fact that my teachers in middle school and high school told me you can never have a square root in the denominator, which was a bunch of baloney because nobody in the real world cares about square roots in the denominator. Does anyone remember a trick related to that? I don't know if you were told this when you were in high school. Do you remember? Yeah, there was this rationalize the denominator trick. Do you remember how to do that? That was the catchphrase.
Yeah, it's like multiplying and dividing root x plus 2 in this case.
Yeah, like in this case, you would use x plus 2 and multiply, like usually it would be in a fraction, you multiply the top and the bottom by the x plus 2. Even though it's not a fraction, we could do the same trick here and it'll work. So I'm going to take root x minus 2. Just inside the absolute values, I'm going to multiply this by root x plus 2 over, really it's like this, right? I multiply by root x plus 2 and divide by root x plus 2. I learned to do this like in 7th grade for stupid reasons because they told me I can't have a square root in the denominator, which is not true. But actually the trick is sometimes handy. My 7th grade teacher would be proud of me. So the bottom, I just have to leave like root x plus 2. But what happens on the top? You now have a difference of 2 squares, right? If you do the FOIL thing on the top, what you'll end up with is x minus 4. And I have removed the square root from the numerator, although I don't know if that seems good to you. But another good thing is I ended up with x minus 4, which is what I wanted to extract from this thing in the first place, right? The goal of the simplifications was that. So I can say just split that out, splitting the fraction up, and then times 1 over absolute value root x plus 2. So the good news is now I can see x minus 4, which is what I wanted to see. The bad news is I have this thing left over here. Any ideas? Here we can do sort of a stupidly effective simplification now. You might be tempted to say you got to do that like, let's assume delta is less than 1 and then do this, that thing, with that trick that we did a lot. It works actually, but there's a much simpler trick. Not much of a trick at all. Would you agree that that fraction right there is less than 1, isn't it? In fact, it's less than a half, right? The denominator there is bigger than 2. So this actually is just, like, that's all there is to it. You don't have to do any fancy business. That denominator there makes it so that other part was less than 1. And I can, of course, when you simplify in these things, you can use equal signs, or you can use less thans. All right, so what am I going to choose the delta to be? Usually I would say, okay, so all we want really is x minus 4 to be less than epsilon. You know, ordinarily you'd have like an extra constant, which you would move to the other side, but there is no extra constant, so I'm just going to choose delta equal epsilon, right? Usually you would use, epsilon over 8 or something, but there is no extra 8 hanging around. So I'm going to say, let delta equal epsilon, then if x minus 4 less than delta, we have, and we begin with root x minus 2. And then according to that same simplification, that is the same as x minus 4 over root x plus 2. But this is less than x minus 4. That is less than delta, which equals epsilon. And that's it. All right. So this was sort of just another example of this limits of a function thing. If you're using square roots, often you have to use that rationalization trick. Really, this was an example of showing that a function is continuous at a particular point, but that really wasn't, the continuity immediately boils into one of these more traditional epsilon delta proofs. So the extra layer of the continuity is not really a big deal. All right, actually, in this case, you can use more or less the same proof to show that this is continuous at any point. 4 is convenient because I know the square root of 4 is 2. But even if you used 5, the same proof will work again. If except use the square root of 5 in place of the number 2. But it doesn't have a big effect. So can I just say similarly, square root of x is continuous at any number c greater than or equal to 0. You have to use a slightly different proof when the c is close to 0, but it's not a big deal. I don't really want to get into it, but it's something that any of us could do. Continuous at any value. So in a situation like that, we say actually the function is continuous on a whole set of values. I'm sure you've seen this definition in calculus class. So given a set, A, subset of R, we say f of x is continuous on the set A when f of x is continuous at every point of A. So continuous on A, come on now. Continuous on A means that it's continuous at every point of the set, right? That's, I'm sure, what you would expect that to mean, all right? I want to say something, a matter of a little bit of subtlety, which I've been kind of ignoring all along. But actually, this is the first time, perhaps the first time in the whole class, that the technical terminology is going to be actually different from the way that you learned this terminology in a calculus class. So it's subtle, though, so it doesn't, this shouldn't really cause any confusion. But of course, we all know every function has a domain, right? And most functions that we talk about, their domain is all of real numbers. But that's actually not all functions have that domain. And it doesn't even have to be a super weird function. Like, for instance, f of x equal 1 over x has domain. Remember, the domain is just all the x's that you're allowed to plug in. This would be all real numbers except 0, right? Which you could write that way, or you could write this way, minus infinity to 0, the open interval union, the open interval 0 to infinity, right? That's the domain of the function. And it is true, f of x equal 1 over x is continuous at all points in the domain. All right? This is not different from what you would have said in a calculus class. The difference is, in a calculus class, usually you say f of x is not continuous at 0, right? In a more technical setting, such as we are in right now, in a real analysis class, you typically wouldn't say that. I would not say 0 is a discontinuity of this function. I say 0 is not part of the domain. So we don't even talk about, is it continuous at 0 or not? That's not a question that can be answered by the definition of continuity, because 0 is not even part of the domain. All right, so to this question, is it continuous at 0? If I was teaching a calculus class now, the correct answer would be no, it is not continuous at 0. But for our purposes, and this is sort of a more technically correct answer, the answer is 0 is not part of the domain, so we don't even consider if it's continuous or not at 0. Really, if you were to try to write down the definition of continuity, what would that mean? So continuous at 0 means x greater than 0, there's this delta greater than 0 such that x minus 0 less than delta implies 1 over x minus 1 over 0 less than epsilon, right? This is f of x minus f of 0. But you'll see this is bogus. Like, you should never even be in a situation where you write 1 over 0, right? So just by asking, is it continuous at 0, you are already introducing something which is undefined. And so the only proper answer to this is x equals 0 is outside the domain So we don't consider if f of x is continuous or not at 0. It's sort of neither, or it's sort of like it doesn't even make sense to ask about that because 0 is just not part of the domain, right? It'd be like asking, is f of x continuous at infinity? The answer is like infinity isn't even a number. You can't plug it into the function, so there's no sense in asking if it's continuous or not there. The function is not defined on that, so it's not anything at, on that point. All right? This might cause you to wonder then, what does it even mean? Like, is it even possible for a function to ever be discontinuous? If not that function, what could a discontinuity even look like? Is there even such a thing? Yes, there is such a thing. A real discontinuity looks like this. A discontinuity would look something like, if I had a function like this may seem stupid, 1 over x if x not equals 0, or say 3 if x equals 0. So now the domain is actually all real numbers in this case, because like 1 over x has a point missing from the domain, but I created an extra point in this definition specifically to fill in the point which was missing. And so the graph of this would look like, the ordinary graph of 1 over x looks like this, which ordinarily would have no value at x equals 0, but I just because I said so, it has this value, 3, right? So that's the graph of this function. And in this case, f of x really is discontinuous, or it is not continuous at x equals 3. And how could we demonstrate that? You always do this with sequences. So you would choose, not at x equals 0 is what I meant. The y value is 3, but that's not important. X equals 0. All right. How you would demonstrate this is by using sequences. You take a sequence which approaches 0 and then demonstrate that f of that sequence does not approach anything, or perhaps approaches something other than the value, something other than 3 in this case. So we need to find a sequence xn approaching 0 with f of xn not approaching f of 0, which in this example is 3, just because I said so. I invented that extra value. Can we think of a sequence which approaches 0 so that f of that sequence does not approach 3? What do you think? You don't have to be too fancy here. A sequence xn which approaches 0. Somebody tell me your favorite sequence which approaches 0. 1 over n is the only sensible answer. Yeah. And then, what is f of xn? F of xn would be 1 over n, right? The function f of x is 1 over x, basically, except for that special point. But these values I'm plugging in do not involve the special point, x equals 0. This is n. So f of xn as a sequence diverges. So it does not converge to 3 in particular. All right? So this is what a true discontinuity point looks like in the technical sense. It's a point where the function does have a value. It's just not, in the calculus sense. The value is not like connected to the rest of the curve at that point. All right. Similarly, we got a few more minutes. Remember this example here? I talked briefly about this example, sine of 1 over x. My 5th grader kid happened to be looking at my screen when I got home, and she saw this graph on the screen. She liked it. For some reason, she thought that was cool looking. Remember this function here, sine of 1 over x? What would you say the domain of this function is? That is the set of all x values which you are allowed to plug in.
R minus 0.
Yeah, I think any number except 0, right? The domain is r minus 0 again, because you can't plug this in. This kind of preempts the question I was going to ask, is that continuous right in the middle? That's an interesting question that you could ask. Actually, it's not really an interesting question. The answer is it's not defined in the middle, and so you don't even talk about if it's continuous or not. What might be interesting is if you filled in a dot somewhere in the middle, then would it be continuous? The answer is no, it wouldn't. But I wanted to look at a similar example, which actually does become a little more interesting. This. X times sine of 1 over x. This is the other picture that I drew last time, which I like the graph of. It looks the same, only it kind of is stuck between this sort of x pattern. So it looks like that. And on the other side also, it looks like that, right? This is a function where it really does look like it has a value in the middle, even though when you just look at the formula here, it's still, the domain is r minus 0, just because the formula has a 1 over x in it. And so you can't put 0 into this function. Even though when you look at the picture, it looks like you might be able to sort of fill in a dot in the middle there. So it becomes a natural thing. And I think we can do this in our remaining 4 minutes. I'm going to say let f of x be this function, x times sine of 1 over x, if x is not 0, and 0 if x equals 0, right? This is that same picture. It looks the same, only it really does have a value right in the middle at the origin. And even though that function is pretty crazy near the origin, I still feel like it should be continuous there. Let's see if we can demonstrate that. So then, in 4 minutes, can we do it? F of x is continuous at c equals 0. Let's see if we can demonstrate that. I better leave the definition there. All right. We got to do this with the epsilons and all that. So I'm going to say let epsilon 0 be given. And then we'll find delta greater than 0 such that. What is this going to look like? I need this setup here. Can someone tell me? It always looks like something less than delta implies something less than epsilon, right? What's it going to be on the left? X minus 0, thank you. That the left side is always x minus c. And then on the right side, should be f of x minus f of 0. What does that look like? Yeah, f of x is x sine 1 over x minus f of 0 is the special value there, 0. All right. Okay, let's do the blue like I always do. I start with the thing on the right. I don't need to write minus 0, right? This is x sine 1 over x. Try to simplify, perhaps using equal signs, perhaps using less than signs, and end up with just what I want to see is this on the left side, which is just x, right? X minus 0, just x. Well, one thing I can do is this. Just I have multiplication there, so we can split it apart. Anybody else see something? Now, you may worry that we're going to have to use some obscure formula about sine of something or other, but it's not so, actually.
Isn't sine always less than 1?
Yeah, in absolute value, the sine of anything is always less than 1. So this, I can just say, is less than absolute value x times 1, right? Anyway, that's equal x. And so we can just let delta equal epsilon. This is like the example that we did before. You don't need any extra constants or anything. It all works out great. So to conclude here, I'll say let delta equal epsilon. Then if x less than delta, we have, come on now, x sine 1 over x in absolute value. This equals absolute value x, absolute value sine 1 over x, which is less than or equal to absolute value x, which is less than delta, which equals epsilon. That's it. So that function, provided you fill the middle point in, really is continuous. This other one, you can't fill the middle point in to make it continuous because there's just too many y values there. All right. We did it. We got 1 minute left. I'm going to let you go early. You get your wish.
Oh, yippee.
All right. Hope you all have a good weekend.